Alright, so let's try and apply our knowledge of electrode potentials to determine the equilibrium constant of a cell. Okay, so let's say I've got some a beaker here, and I'm going to chuck in a zinc electrode and a copper electrode. And what I want to know is if I connect these electrodes up, firstly, will electricity flow? Will electrons flow? And we can deduce that from the Nernst equation. But also what I want to know is what is the equilibrium constant? Is zinc more likely to go into solution, or is copper more likely to go into solution? And so we disconnect, and what we're going to do is we're going to measure the potential, the voltage across these. So we're going to attach our multimeter, and we're going to measure a voltage when this has reached equilibrium. So I mean, when you first connect this up, electrons are going to flow just because the number of because there'll be a different number of zinc molecules in here and a different number of copper atoms in the solution, copper ions in the solution, and so you'll eventually reach an equilibrium. Now, at that equilibrium, no electrons are flowing, and we can measure what the equilibrium potential is over those two electrodes. And so what we can do is measure this voltage, and it's about 1.1 volt. And this is how I'm going to explain how we work out this number here. So E0, which is the voltage when the equilibriums are basically equal, and when that quotient is 0, when there's no difference, when everything has reached equilibria, we will measure this voltage, which is 1.1 volt. Now, what we do is we look at our table for copper and zinc, and we look at the cell standard potentials for that at 298 Kelvin, and we note that copper 2 plus going with 2 electrons going over to copper solid, the electrode potential for that is 0.34 positive, and for zinc 2 plus 2 electrons going to zinc metal is negative 0.76. Okay, so these are the two numbers. So what you do is basically work out the difference between these two numbers. Okay, so this is negative 0.74, and we've got a positive 0.34. And so the difference between those, the difference in the electrode potential is 1.10 volts, which is what we measure. And so basically you can see that there's some kind of arbitrary voltage that we've set in the middle, and we've just said, well, that's lower than this arbitrary voltage, and then this is higher. Now what we do is we set this voltage here, negative 0.74, as our zero voltage, and we measure up from there. Okay, so this is where this is the standard standard potentials, but in the case of our little cell over here, this is the voltage that we measure across that. Okay, and so that's how we use the standard potentials, and I think this is done using hydrogen reference platinum. We get that voltage there. Now, when we've reached equilibria, our quotient, or our reaction quotient, now becomes constant, and so we now define something. So three lines indicates a definition as K when we've reached equilibrium. Now, this is called our equilibrium constant, constant, and basically it basically says that what is the equilibrium constant when this has reached equilibrium, which is very helpful. So we've got let's write out the Nernst equation: E naught minus RT over ZF log of now K. So what does K mean? Well, in thermodynamics we looked at K. K is the equilibrium constant, and it's the concentration of the products divided by the concentration of the reactants. And so if we've got a large value of our equilibrium constant, it means that there are many more products than there are reactants. If we've got a small K, then we've got a large number of reactants and very few products, and so the reaction is favoured in the left direction. Okay, so this here at equilibrium is going to be 0 volts because there's going to be no current being produced, and we've measured this, and this is 1.10 volts. We can also calculate that from our standard potentials. So we can rearrange this equation. E naught is equal to RT over ZF log of K, and we have to remember that this is for the reaction copper 2 plus aqueous plus zinc solid going to copper solid plus zinc 2 plus aqueous. Okay, and we remember that this is actually an equilibrium, so it can go both directions. And what we want to know is what the equilibrium constant for this reaction is, and what is actually consumed. Is the zinc consumed or is the copper consumed? So that's what we want to know. So if you put all the numbers in, and this is 298 Kelvin, then what you end up getting is that K is equal to 1.5 times 10 to the 37. And I should also note that you have to remember that this is actually 2 because we've got 2 electrons involved in this reaction here. And you can see that up here, there's 2 electrons needed. So as you can see, the equilibrium constant for this reaction is very, very large, which means that at the end of this reaction, when we've reached equilibrium, we're going to have far more products than we do have reactants. And so that means that zinc is preferentially reduced to zinc 2 plus. And zinc is oxidized to zinc 2 plus, and copper 2 plus is reduced to copper, because remember that oxidation. Oh, running out of memory. Is loss of electrons, and so zinc here is losing electrons and becoming zinc 2 plus. Copper 2 plus is gaining electrons and becoming copper metal. So that's a good way to remember it. Often with these binary memorizations, it's much easier to memorize only one side of the system, and that helps you to memorize it. So that is basically how we use the cell potential in order to work out equilibrium constants.